Okay. So we have discussed on the immediate settlement, primary consolidation. Okay, now we move to secondary compression. Okay, even after complete dissipation of the excess pore water pressure and the effective stresses are about constant, there will generally be further volume changes and increased settlement, which is termed as secondary compression. Okay. So once we have once the soil complete the primary consolidation, okay, so it may continue with the secondary compression, okay, due to the readjustment of the soil fabric, okay. So the soil fabric will be readjust their position, okay. So in that case, the secondary compression occur. Okay. So this is the formula for the secondary compression, okay, where the C alpha or CS is secondary compression index, okay. So the rest is the HI, okay. EP is the voltage of the end of primary consolidation. Okay, time for calculation. Okay, so later on, I will share one example. Okay, on to calculate the secondary compression. Okay, and upload on the e-learning next week. Okay, so this is for the secondary compression. Okay. So the secondary compression ratio or modified secondary compression index can be estimated from the relationship proposed by Mesri. So Mesri has proposed this kind of relationship, okay, where we can identify the value of the modified secondary compression index based on the natural moisture content. Okay. So means that this line, okay, is considered as the relationship, okay, for the moisture content with the modified secondary compression index. Okay. So they use the log graph, okay, to um, propose for this secondary compression index value. Okay. So either we can determine from what we call from the odometer, okay, or we can use this value to determine the secondary compression index value. Okay. So that is for the consolidation process. Okay. Now we move to the rate of consolidation. Okay. For one-dimensional consolidation with vertical drainage, the degree of consolidation UV is a function of the time factor TV. Okay. So we may use this equation, okay, to determine how long the process of consolidation, especially on the primary consolidation, will complete. Okay. So TV is the time factor. Okay. Normally, when we want to estimate for the 100% of primary consolidation, okay, we use the degree of consolidation as 90%, okay, because we can say that it's almost complete when it reach consolidation degree of 90%. Okay, so when the 90% of UV, the TV will equal to 0.848. Okay, so this 0.848, okay, we may put in the equation. Okay, so the CV is based on coefficient of consolidation. Okay, so this CV we may obtain from the odometer test. Okay, so we need to determine the average CV value. or we may use the CV based on the applied stress that's similar on the site. Okay, so then we put the CV here. Okay, so when we want to estimate the T, okay, so we move the T on the left side, so the TV on the right side. Okay, so the HD, it depends on the what we call as on uh, the thickness of the clay layer. Okay, and it rely on the drainage system. Okay, for example, okay, this is the clay layer. Okay, so the clay layer is okay is uh, encapsulated with sand soil, overlain and underlain, okay, by the sandy soil. Okay, so in this case, it is a double drainage system. Okay, so the soil or the water can move upward or downward. So the HD should divide with 2. Okay. So let's say if this is a bedrock, okay, so usually the bedrock we consider as an impermeable layer. Okay, so when it is an impermeable layer, means that it is a single drainage system. Okay, so if a single drainage system, so the HD we divide by 1 or it is equal to H. Okay, so we call as a drainage path length. Okay, so it is single drainage, so it is the height is similar to the height of the clay layer. Okay. So the coefficient of consolidation can be obtained from odometer test at the level of effectiveness similar to those anticipated under embankment loading. Okay, so we need to get the value of the CV based on the similar effective stress because the CV it rely on stress applied on the soil or on the sample. For example, we start first with 3.25, okay, then we increase 6.5, 6.25 as well, so 3125. Okay, then we increase up to 12.5. Okay, so double to again 25. Okay, double 25 at 50, 100. Okay, until we it increase up to 6,400 kPa. Okay, so it depends. Okay, for example, if the embankment load is around 100 kPa, so we need to refer to the CV from the 100 kPa stress. Okay, so another reliable way to determine CV is from the field in situ probability test together with MB from laboratory odometer consolidation test. Okay, so beside of the use of the CR or CC, okay, there will be another coefficient which is the volume of coefficient of compressibility, volume of compressibility. Okay, so we obtain from the EP graph. Okay, while the CC and CR we obtain from E log P. Yeah? So we have two different approach. Okay, so first we use the E log P to get CC or CR, and another is to use the EP to get the MV. Okay, both of the parameter could be used to determine the settlement. However, most of the designer prefer to use the CC and CR. Okay, so once we obtain the MV, so we also can estimate the CV. Okay, so it depends on the type of the permeability. It depends on the permeability value. and also the density of water. So we can use 9.81 or 10. Okay. So then we can obtain the CV. Okay. The use of the field value of K will give a better representative effect on large-scale soil structure and probability not able to be reflected in laboratory tests. So it is recommended to use this value rather than we use the odometer CV from the odometer. However, it depends on the cost that we may invest. Okay, so for example, to get the probability from the field, so we need to dig a well, a small well, okay, or hole, okay. So we need to have a 2 hole, okay, to determine the what we call the K value at the field, at the site. Okay. So it is very time consuming because we want to get a constant value of K. Okay. So for example, we need to count for the decrease for the difference between two hole. Okay. Based on the groundwater level. Okay. Since the permeability and compressibility of the soil reduced with increase in effective stress, the value of CV should be modified to reflect the state of stress over the period during which settlement rate are being calculated. Okay. Okay. So method for embankment construction. Okay. So I will list several methods of embankment construction. Okay. So for the first one is modification of embankment geometry. Okay. The reduction of slope angle or embankment of counterweight berms improve the stability of the embankment by increasing the length of the potential failure surface in the soft soil. Okay. So means that we may increase the length of the slope. Okay. By construct the counterweight berm. Okay. The weight of the shallow slope of berm counterbalance the disturbing moment of potential failure surface under the embankment. Okay. The field should be raised equally across the embankment. However, this method has disadvantage of greater length and volume of field are needed. Yeah, because we because we may increase the width of the slope. Okay, so we need to make sure that where is the boundary of the or the limitation of the embankment itself, the area. Okay, so and then we also need a huge volume, okay, to fill the to construct for the counterweight berm. Okay, so this is not recommended unless we want to invest, okay, on the fill material. Okay, however, if the boundary is very limited, so it's not wise to use this approach. Okay, so excavation and replacement of soft soil, okay, total or partial. Okay, the very soft compressible cohesive soil are excavated out and replaced with better material. Okay, so we need to identify what is the type of the material. Either it is unsuitable material or suitable material. If it is unsuitable material, so we need to excavate and replace with suitable material. Okay, that provide a stronger and less compressible foundation. The experience on highway construction indicate that the excavation and replace depth up to a maximum depth of 4.5 meter is viable in terms of cost and practicability. Okay, so the maximum is allowed only up to 4.5. More than that is very costly and it's not practical. Usually, the excavation should extend to at least to the toe of the embankment and beyond to increase the stability of the embankment. Okay. So, for example, if this is the embankment, okay, so the replace and the remove of the replace should greater than this area. Okay. Should have we need to have some uh, length, okay, because it should extend to at least to the toe of the embankment, okay, to ensure the stability. Okay. So if the soft material is much deeper than the practical excavation depth, partial excavation and replacement is also possible. However, the effect on stability and long-term settlement of the remaining is considered. Sometimes partial excavation and replace of soft material is used with the other ground treatment to overcome the problems. This method will be more difficult if the groundwater level is high. If pumping of water is not practical, then compacted suitable material cannot be used and the underwater replacement material should be used. Okay. So the other way is to use the partial method. Okay. So for example, if uh, the embankment, okay, and the depth of the we call it the soft layer, okay. So we may excavate partial, okay. Then might be we can use any ground treatment method, okay, until it reach the hard layer, and then replace with the suitable material and then construct for the embankment. Okay. If the soil material is deeper and the practical excavation depth partial, okay. However, okay. Sorry, this is a repeated statement. Cut. Sorry. Okay. Okay, the main disadvantage of the mistake is the amount of the soft soil which need to be disposed. Okay, at the same time, to replace, we also need to have a huge volume of suitable material. If the existing material is near, so there will be no big issue. However, if we need to import from a very far area, so there will be may increase the cost of the project. Okay. So excavation and replacement of soft soil, okay, is also demonstrate that by remove the top 0.5 meter to 2 meter very soft to soft clay, the subsoil settlement is reduced by 27 and 60% respectively compared to no ER. Okay, so this just an example. Okay. So this sorry. Okay, this is without the ER. Okay. So the settlement up to 0.8 meter. Okay. So when we do the RENR, okay, so we can reduce up to 60% of settlement. Okay. So this is after after the example show that after the soil has been removed up to 2 meter. Okay. So the thick of the soft layer is about 15 meter. Okay. With a 2 meter height of embankment. Okay. So it reached 0.3, okay, which is the allowable settlement from our previous discussion. Okay. We need to look again. What is the allowable settlement? Okay, should more less than 250. Okay, so in this case, it's still more than 250. Okay, so it's still more than 250. So perhaps 3 meter or 4 meter is required for the ENR, because the maximum is 4.5 in the practical one. So perhaps it can reduce to less than 0.25 meter. Another reason is the strength of thin top crust is not reliable and will be disturbed and weakened during construction due to movement of construction machinery and shocking. Okay, so there is a two example what two reason okay what why we need to remove up to 2 meter up to certain depth and replace. Okay. Okay, the second one is the third one. The third one is the vertical drain. Okay, vertical fabricated band shaped drain are installed through soft clay soil to accelerate the speed of consolidation of the subsoil by reducing the drainage path length and utilizing the naturally higher horizontal permeability of clay deposit. Prefabricated drain using corrugated polymeric material, polyethylene and polypropylene for the core, and woven or non-woven fabric or fiber to the filter. Okay? So that is the material made for the vertical drain. They are about 100 millimeter wide, 4 millimeter thick, and are installed using the closed-end mandrel and usually to a depth up no more than 30 meter in very soft soil or 10 minutes shorter in strong material. Okay, so the maximum length, okay, uh, for the vertical drain installation, okay, is when it reach SPT number 7 to 10. Okay, if but it can install up to 30 meter deep. So that is for vertical drain. Okay, then we have here temporary surcharging. Okay, temporary surcharging is to subject the ground to higher pressure than that during the service life in order to achieve a higher initial rate of settlement, thus reducing long-term settlement. Usually, these methods are used to control both total settlement and differential settlement at the abutment to bridge or flyover where culverts are crossing beneath the embankment. Usually, surcharging is also used together with prefabricated vertical drain installed into the low permeability soft compressible layer. Okay. So normally it is a combination between PVD and also the surcharging methods. Okay. So this is the concept of surcharging methods. Okay. Vertical pressure from embankment loading. Okay. So during the construction, okay, the pressure increase. Okay. So then it will remain constant. Okay. So for instance, after they remove the surcharge, okay, so it may remain on the permanent loading. Okay. So during the service life of embankment, so it rely on the permanent loading. Okay. While for the settlement, okay, the settlement will increase, okay, during the what we call during the construction. Okay. So during the surcharge period, okay, so if we reach the primary consolidation, okay, so let's say if the surcharge has been what we call if the surcharge is constantly applied, okay, so it will be shown in the dash line. Okay. If the surcharge has been removed, okay, so it can show this solid line. Okay. So this dash line, okay, show that without the surcharging, okay, So at the end, it may cross the same what we call as permanent loading line. Okay, so means that during the service life of amendment, it's not necessary to have this surcharge, okay, because the settlement has been reached the primary consolidation. Okay? So it is enough and not compulsory to include for the surcharge because means that the settlement has been completed. Okay. Okay. Geotextile vessel reinforcement. Okay. This is the method that we want to make sure that stability at the foundation level. Okay. Geotextile vessel reinforcement is used to allow higher embankment to be built without compromising the embankment stability during construction. Okay. So I have mentioned previously that this geotextile will be installed at the bottom of the embankment structure. Okay. So another one is the stone column method. Stone column method will utilize as a ground treatment once the combination of excavation and replacement, PVD, temporary surcharge, and the geotextile vessel reinforcement are found not viable. Okay, so means that this will be another approach where most of the of the conventional method is not work well. Okay, so the present of the stone column creates a composite material of lower compressibility and higher shear strength than the in situ very softly. Okay, so it is look like a pile method. However, okay, uh, the strength or the stiffness is less than the pile uh, material. Okay. So this is the last option, okay, where the application of the pile embankment. Okay, at the area of very soft clay, where the other ground treatment are not suitable to support the railway embankment, pyrite are used as a ground treatment and settlement reducer. Okay, so this is the some of the illustration of the pile method. Okay, so this is without the what we call it the pile method. Okay, so this is after introduce the pile, okay, where it can reduce the it can reduce for the long term settlement problems, okay, compared to the first one. Okay, so the culvert founded on pile foundation, okay, this also not recommended. Okay, uh, it's the culvert should what we call it to construct at this almost at the same level of the final profile. Okay. Okay. So construction monitoring and control. Okay. So during the construction of the embankment, okay, so several measurements should be taken. Okay. For example, the vertical settlement. Okay. Then the horizontal movement and the development of pore water pressure. Okay. So for the vertical settlement, settlement gauge on original ground surface or base of excavation. Okay. So for example, this is the what we call this is the vertical settlement. Okay, marker. Okay. So settlement marker on surface of field of ground outside the embankment. Okay. Full profile settlement gauge under the embankment. Okay. Subsurface settlement gauge or extension meter in the subsoil beneath the embankment to measure settlement of different depth of the subsoil. Okay. So that is for the vertical movement. For any vertical movement, okay, we may use what we call a settlement gauge okay, extensiometer, okay. Okay, while for the horizontal movement, okay, so we should consider when we want to look on any horizontal movement, okay, for example, like this one, okay. So inclinometer in the subsoil and should be installed in this area, okay, to monitor the sliding effect, okay. Displacement marker at the top and the toe of the embankment, okay. So then the last one is the piezometer at several depth and location in the subsoil beneath the embankment, okay. So for example, this is the piezometer P1, P4 and P5, P4, P5 and P6. So then they also put in the what we call it in the at the toe, okay. So this piezometer, okay, we may monitor, okay, during the loading process or the filling process, okay. Because for the common what we call it pore water pressure development, okay, similar like this, okay. So with the depth, so this is the pore water pressure, but this is the depth, okay. So when we install or we include the we apply the embankment, so there will be a slight changes of the pore water pressure, okay. So the difference should not greater than 0.7. 0.7. If greater than 0.7, so there will be a potential of failure happen on the foundation. So means that we need to monitor, okay, and it should not greater than 0.7. Then we need to let it stable, okay, by let it by let it stable for a certain period of time. Okay, so we need to monitor. And then once start we increase again, okay. So we need to monitor the development, okay. So that is the way how we monitor the pore water pressure, okay, by using the piezometer. Okay. So embankment stability check during construction, okay. So this is based on modified Matsuo stability plot, okay. So they identify based on different zone. Okay, they have a green zone, yellow zone, orange zone, and red zone. Okay. So for example, when we apply a load or fill height, okay, so we need to determine what is the lateral displacement. Okay. So if still in the green zone, okay, embankment filling can continue. Okay. Supervise, okay, if it is in the yellow zone, this area, okay. So supervising engineer to inform design office embankment filling can continue. For area with PBD, the embankment filling rate reduced to 0.5 meter per week. Okay. So we need to monitor. Okay. So when it reach to orange zone, supervising engineer to inform design office immediately. Embankment filling work only can proceed with permission from the design office. Okay. So supervising engineers to stop the embankment filling immediately and inform the design office when it reach the red zone. Design office to review instrumentation data and advise on next course of action. Okay. So this is this is the approach, okay, by looking at the lateral displacement, okay. The one that I discussed previously more on the pore water pressure. Okay, this is more related to settlement or lateral settlement. Okay. Construction monitoring and control. Okay. Control or measurement settlement. There are two commonly used methods to interpret the measure settlement. Okay. The first one is the hyperbolic method, and the second one is the Ashoka method. Okay, so we can either use both. We can either use hyperbolic or Ashoka method. Okay, in 2013, okay, I made this Ashoka at Nagoya. Okay, during a conference in Japan. Okay, okay. So he has this method, okay, for embankment or for settlement monitoring for embankment. Okay. Design of surcharge. Okay, surcharging is to subject the ground to higher pressure than that during the service life. Okay, in order to achieve a higher initial rate of settlement, those using long settlement. When designing surcharge, three major issues need to be addressed. Require duration required for surcharging, height of extra field on the top of the embankment required for surcharging, bearing capacity check for the embankment at the each with surcharge field, okay, the gross thickness of the field which include embankment and surcharge field in terms of gross field height. Okay, so this is when we apply a surcharge. Previously we discussed on the normal preloading. Okay, so this is when we apply a surcharge. Okay, so I guess the same approach. Okay, when we apply the surcharge, we need to consider also the long-term settlement. Okay, so determine the duration allowed for surcharging depend on the project development schedule. Obtain the total settlement versus time plot for different gross field height as follow. Okay, design on the figure below using the total settlement. Okay, and allow. Okay, this is the what we call it, the 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 diagram. Okay, if vertical gate are used, then this method can also be used with minor adjustment for vertical spacing and more rapid rate of settlement. Okay, so this is the way that we monitor the effect of the surcharge. So from there, we can estimate what is the required surcharge duration and what will be the required height of the surcharge. For this example, the surcharge will be end at the 6 month. Okay, we target to end at the 6 month. Okay, with the field of the surcharge is 3 meter and the long settlement reach the amount of settlement that we needed. Okay. So actually this can be carried out by using a manual calculation. Okay. We may use the one consolidation equation, okay, to plot this kind of graph. Okay. So it's not necessary for us to use what we call as a software to get this graph. We can use a normal Excel. Okay. So stability analysis, for stability analysis, at least two stages should be checked. Okay, short term, long term. Okay. Where the factor safety for the stability short term should greater 1.2 and should greater 1.4 for the long term. Okay. So we can use the circular or non-circular method. Okay. So in stability analysis, the following dimensions should be used. The height of the embankment should be embankment field height if no surcharge, gross field height if surcharging. Okay. So we call it as a gross because later on we may remove the surcharge. Okay. So at least, okay, for stability, okay, this is for stability. Check at least for the settlement, no need to include the surcharge, what we call the traffic. Okay. So for the stability, we need to include the effect of the traffic. Okay. Because the settlement is a long term. The settlement is a long term. So if we include the traffic, so it may overestimate the settlement value. Okay. So the magnitude of the imminent settlement, both in soft clean circuit, should be included in the embankment field to simulate the settlement. Okay. The guide the general guideline for the strength parameter of the well compacted predominantly C is equal to 0 to 5, C is equal to 28 to 30. It's recommended to carry out shear board test on the well compacted fill material to obtain representative parameter. Okay. So normally when the slope angle is less than the phi value, if for a very well compacted soil, so there will be no issue. So the stability of the slope is considered as safe. However, the foundation should be checked, the bearing capacity. Okay. Okay, so this is a common stability analysis where we have a bishop, circular, jumbo, non-circular, Morgenstern price, non-circular, Shaman, non-circular, and normally we may use the what we call as the software. Okay. So in general, there are three types of method in modeling the soil in the stability analysis. Okay, total stress, effective stress, and shear strength. Okay. So total stress, this is what we have learned in the slope stability. No need to explain more. Okay. So this is based on effective stress. Okay. So this is very unfamiliar use. Okay. Which is the undrained strength developed by lab and food. Okay. Unlike effective method, the power to pressure sharp during shearing to failure need not be estimated. Those eliminating an unknown in design procedure. This method is most commonly used in analysis for short-term stability and design for stage construction. So this is similar to what used in the total stress analysis. Okay. So factor safety, generally in practice, the factor safety on shear strength from total stress or undrained usually is temporary because it is a rapid test. So 1.2 short term, 1.2 to 1.3. Okay, for the long term, so 1.4 to 1.5. Okay, so this is just a repeat explanation on the stability for the slope. Okay, so selection of ground treatment for stability of the embankment. Okay, so to begin with, we look on the priority number 1. Okay, either we use the counterweight berm. Okay, however, it need to rely on the right of way, the boundary. Okay, infill material are sufficient at site. Partial soft soil replacement. Okay, so this is what we call as E and R. Okay, or we can combine both together. Okay, so then later on, if the priority number 1 doesn't work, okay, so we may use the surcharge vertical drain. Okay, geosynthetic. Okay, at the base of the embankment. Okay, or we can combine D and E. Okay, so the last one is the pipe embankment using slab system. Okay, expanded polystyrene, stone column, dynamic displacement. Okay. Okay, so that's all for the embankment construction. Okay. We may have the last lecture on the next week. Yeah, because I could not finish the instrumentation by this week. Okay. So I guess that's all for today. Okay. So we meet next week. Okay, I will try to provide an example on the embankment calculation. Okay. So with that, I end our today class and we meet next week. Okay.